I'm Nathan Saichek. I'm the CTO of Longshot. Everybody calls me NATO.
Yeah,
so,
just for the obvious
call me
reasons,
NATO.
or?
No, when I was a child, I was a very chubby baby, and my parents called me NATO Potato. And then in high school, I was not chubby, and they dropped the potato part.
You lost your potato.
I know, it's crazy, it's crazy. Now I've got a new one.
You got a potato gun.
Big potato gun.
Yeah.
It is very, very similar to a potato gun that any
decent child,
decent high school student or middle schooler would build. A little bit bigger, and there's a few features of it that are a little bit different. But starting with, we have a compressed gas tank. This is just a commercially available compressed gas tank that we bought, and then we cut the end off of and put a flange on the end so that we could bolt it up to pipe. At this end of it, this is our feed line that comes in. So we have a high pressure line, and we have a pressure sensor here, so we can basically tell what pressure we're running at as we fill the system. To the end of that is welded this flange, and that connects to the breech connector that connects to the barrel. So in between here, this is where we put our triggerable burst disc. So that's holding back the high pressure. This is just sitting here at atmospheric pressure. And then here's another gasket that's a Mylar disc that's holding the vacuum for the barrel. So the whole barrel gets evacuated. So this is holding vacuum. This is ambient air pressure, and then this is high pressure. And when we want the system to fire, we pop the burst disc, and then that high pressure air blows through. It pops right through that little Mylar disc and hits the projectile and starts the projectile on its journey. This is what it looks like when it's pressurized, but doesn't actually rupture. What you're looking at is a bunch of layers of stacked up Mylar. So I guess I should preface this with, we spent about a year trying a bajillion different ways to pop burst discs. And this is one that we found that was one of the simplest and most reliable, but doesn't scale to large geometries. So we have another technique that also works at small scale, but that also works at large scale. But this was the one that we first got working, and so this is how we built this system. It's a stack of Mylar discs, and in the center of it is a small bit of wire, and we dump a capacitor through that wire, and the wire explodes and ruptures the Mylar, releasing the gas.
Okay, and then I'm gonna mess this up, but the point of the burst disc is to kind of hold back some gas until the projectile is coming through, and then you blow it out to let that gas go on either side of this.
Oh yeah, if it's the wedge thing, then we want it to squeeze the wedge. Right now we're just pushing from behind, so we just wait until the projectile's just past the burst disc, and then we release some gas. But we'll get there. Right now, as far as this thing's concerned, the projectile is sitting static right here, and we have just a burst disc sitting here holding back 850 PSI.
And that's just letting that first.
And that's just going to let that first thing go.
But then there's one of those at each of these three different.
Exactly.
What do you call those again?
Boosters.
At the boosters. So there's one of those. That's kind of the key to each booster.
Right.
Is letting this burst in. And the thought was that when you guys move from this to the bigger systems, I mean, it would be awesome if you had a valve that just instantly opened and closed.
Exactly.
But if it's big, at the speeds you need that to go, it's just not physically possible just to have some valve open and close. So you have to do this kind of more percussive, explosive operation.
Exactly, yeah. And so the speed at which these things open is roughly, can be approximated by the crack speed in the material. So Mylar is a pretty brittle plastic. It opens very fast. Steel, the crack propagation speed in steel is about 5 kilometers per second. So that opens really, really fast. So we want basically a somewhat brittle material that'll open quickly. It starts off, basically mounted in the barrel about here. We release the gas, it starts moving. This is a position sensor that detects the projectile passing by. We're recording data at a megahertz, 1 million samples per second. And so if we were just recording 1 million samples per second all the time, we'd be getting gigabytes, terabytes of data, most of which is blank, empty, useless crap. So we use this to trigger the projectile's moving. Now we actually care about what our sensors say. And so the projectile comes along here.
It's moving.
It gets to here. And we have another basically set of these sensors here that detect the projectile. And those are used to trigger the burst disc. So there would be a burst disc here with a booster. And so as soon as the projectile encounters these things, we pop the burst disc. A big dump of gas comes in right behind the projectile and starts accelerating it harder, and it moves along. And we get to this booster, and the same thing happened here. For this past test shot, what we had is we had a high-speed camera looking at a big sheet of plexiglass looking through here so we can monitor the projectile as it came by.
Oh, wow, yeah, you can just see right down it.
Yeah, just look in there. So we have this rig set up so that we can do that, collecting data at a halfway point, basically. But again, we have the sensor that would detect the projectile, pop another burst disk, projectile cruises on down, get to the third booster. Again, same story. Also, again, here we have another set of vacuum pumps and a vacuum valve. So the projectile comes along, we add another blast of gas, and it cruises on down and out the muzzle. And then we hit the safe, and you've seen the results of that. In here we have another. This is where we put our high-speed camera. So inside there, it's looking at a little mirror that's looking perpendicular.
That's cool.
So we get as the projectile goes by, we can get high-speed footage of the projectile leaving the muzzle, which we can count frames and say, oh, here's how fast the projectile was going. We can see it went, across the frame in this many, milliseconds or microseconds.
And every time you do this, then you have to replace the burst discs.
Yep, replacing the burst discs.
You just take off
just
the
unbolt the dozen bolts, take the booster off, pull the burst disc out, new burst disc in, booster back on, bolt it back up again.
It seems crazy, at least in my head, that the sensor could track this thing going that fast and like make anything happen in time for.
Yeah, the real magic is basically inside our pop carts. So we have these carts that have a bunch of like small amplifiers. So there's this thing generates a little signal. There's a little, if you went out to a gun range and you wanted to know how fast your gun was firing, they sell little, things you can clip to the end of your gun that'll detect the projectile. And we basically have exactly that, but just an in-house built version of that. So we can detect the movement of high-speed ferrous materials.
Okay.
Or not necessarily ferrous, but anything that's electrically conductive, we can track it down the barrel, which means, fortunately, we won't accidentally trigger. It takes a pretty significant amount of conductive material to trigger the system. But once that thing passes by, we detect it, we send the signal, and basically in about 3 microseconds, we dump approximately 1 kilojoule capacitor. So that's basically like about 100,000 amps gets dumped in a couple of microseconds, and that opens the burst disk.
This is weird because like on the one hand you're saying this is like a fancy potato gun, so
Right.
it comes off as simple, and then obviously you've built custom.
Right. A
bits
lot
and
of the
pieces.
hardware is simple, and then there are a few things that are like kind of fancy.
Well, and so what I was wondering is, I mean, like when I'm hearing you describe that, or we're seeing the burst disc, just in my head, I'm going, okay, that must have been the stuff that was like some of the hardest to engineer. What's been the hardest thing
What's
to
funny
figure
is,
out?
I would say detecting the projectile was pretty tricky. One of the things we used initially was a photo gate. So we'd have an LED and a photodiode, and when the projectile would come through, it would block the LED, and we would use that to trigger. And that worked pretty well. The problem is that, like, when you have a big blast of gas coming through, sometimes just the shockwave of the gas would distort the signal enough that it would trigger prematurely. These new sensors work much better than the photo gate-based sensor. Detection and triggering was hard. Getting enough energy into the burst disk was hard. We tried a whole bunch of different things, SCRs and IGBTs and all kinds. I could use a bunch of electronics terminology, but MOSFETs, basically big MOSFETs. We ended up going back to technology that's been in use since the 60s, vacuum tubes. We have vacuum tubes that we use that can dump that energy. Yeah, I'll show you one inside. It's called an ignitron. It's it's a vacuum tube about this big, and it's got a puddle of mercury in it, and that actuates, like I say, in a couple of microseconds to dump all that current.
To dump the current,
just to release the burst disk. Yeah,
okay.
Burst disk.
Okay.
So I would say that, like, popping the burst disk has always been the hardest part. And then there's a few other things that have been, tricky or finicky that it's just taken a lot of like seeing all of the failure modes and fixing all of them. And then eventually, once you've ruled out every possible way the thing can't work, then it works.
When I was like reading about this and thinking about it, as you get to these much longer versions of this, I mean, you have 3 of these boost waypoints right now where you have to do this ultra precise operation.
Right. 10 kilometers.
10 kilometers long.
Yeah.
You're going to have
a lot more.
Like hundreds,
thousands Yeah.
That all has to be sequenced. Does this projectile makes it all the way along, doing their job? So I had two questions on that. Like one is making that work, and then two is you have to replace a burst disk. You don't want this to be a manual operation across thousands of these, right?
Yeah. Right now, it takes like an hour for us to replace all the burst disks. A couple of techs come out here with some torque wrenches, and it's good. When we have a lot of them spread out over kilometers, that's implausible. So we've already developed a hydraulic clamp mechanism. So basically we can push a button and the clamp releases, you pull the burst disk out, put the new burst disk in, you push the button, clamp's closed again, you're set.
And it would be, the whole thing would be automated?
The whole thing would be automated,
okay,
yeah.
okay.
It might be that like initially we still have somebody go out to each one and replace the burst disk, but they're not unbolting anything. They're just pulling the burst disk out and putting the new burst disk in. And then eventually, like that works fine if you're trying to fire like once a week or something like that. When we want to fire once a day or multiple times a day, then we probably have like a cartridge full of burst disks and we just replace the cartridge once we've done every 10 shots or 20 shots or whatever. And there'd be some set of, hydraulic mechanisms or pneumatic mechanisms that pop the old burst disk out and pop the new one in. That's going to be a fun engineering project, but that's like, 5 recent grads can do that project. That's industrial automation. That's a pretty easy problem to solve. The other side of the question is when we have a shit ton of burst disks, how do we make sure that they're reliable enough? And that basically is a mass manufacturing and reliability question, which involves things like having a nice assembly line with checkpoints and quality control and manufacturing standards and work instructions and automating as much of that as possible. And so we will at some point be setting up assembly lines for burst disks, and we'll have quality control, and we'll sample every, 20 burst disks, we'll pull one out and test it and make sure that it works properly and stuff like that. Again, these are like just sort of standard industrial processes. If you're mass producing an iPhone, what's the yield rate on building an iPhone?
Right. If we can make semiconductors, we can make burst disks.
Right, exactly. It's not a fundamentally complicated thing, and they get much simpler. This is actually like about as complicated as we think the burst disks will ever be. The ones for the future are made out of steel, and the burst disk itself is much simpler. We've pulled the popping mechanism off of the burst disk itself into an external thing. And so there's like a separate piece. And so we can test those separately, and we test the burst disk separately, and should all just, again, hopefully it just works. And then as far as keeping it reliable and synchronized, one of the main things that we do as sort of an engineering philosophy is we keep software out of everything that we can. So this whole system, there's no software involved in any of the control loops. We monitor things with software, but when this system goes, it is analog signals that trigger circuits that just do their job. It's all like custom single purpose things that there's very few things to fail. When you've reduced the number of things that can fail, then things tend to work better. So when you have really high reliability systems, you want to just reduce the number of components. We don't want to have an out of memory error on our operating system mean that our burst disk doesn't fire. We're not going to have that happen because there's no computer in the loop. So we keep our control loops small, tight, and simple so that they can be fast and reliable.
You say it so confidently. I appreciate that. There's technical challenges ahead, but
absolutely.
You feel like these are nothing is even new things really need to be invented. Like new material science.
Not on the Canon side. I'd say the projectile is going to be a different project. Like the Canon side is basically, I think Mike said it, like a civil engineering project that's disguised as an aerospace project.
Yeah.
The Canon is pretty simple. The projectile will be more complicated because we're going to, testing it is hard. Fortunately, we're going to be building a system that's designed to test hypersonic systems for cheap. So that'll be great for testing our projectile. That's the whole sort of the next step is that Nevada test system that'll let us test projectiles and projectile systems, guidance systems, heat shield systems, radio systems, communicating radio out through the ionized gas field around a hypersonic projectile is challenging. Starship recently demonstrated it was freaking amazing, that re-entry. Amazing being able to see something that's like surrounded by a shield of ionized gas and it's still transmitting, radio because they could transmit it up instead of down. That's amazing. So we'll have the same kind of challenges and we'll have to, find solutions to them. So that part will be more challenging. But, again, I think we're setting ourselves up for success.
After Nevada, when would be the first version that sends something to space?
To space, exactly. We're going to go to Nevada. We're going to build something that's like this, but much bigger. All the architecture will be the same. We'll have, boosters that are 2 cubic meters of volume instead of, a couple hundred cubic feet. So the whole system basically will just be much larger. We'll have a 30-inch diameter barrel that'll be, I hate to mix units, about 500-600 meters long. And that system will get 100 kilograms to Mach 5, 20 kilograms to Mach 7. The next stage is to build something that gets those similar masses up to Mach 15-ish. So we'll take that gun and then we will extend it with the side injectors. So we'll be able to get just pushing from behind the way this one does. This gun just pushes gas from behind. That can get us up to Mach 5, Mach 7. If we want to go faster than that, then we have to squeeze the tail. So the Nevada system will probably have about 30 boosters, 25 to 30 boosters to get the projectile up to Mach 5. And then after that, we'll add side squeeze boosters that they'll get the projectile up to Mach 10, Mach 15. We're optimistic that the Nevada system will be able to extend it enough that we'll be able to get up to Mach 10, Mach 15 with that same system. Or if not exactly the same system, we'll build it at the same site and it'll just be next to the Mach 10 gun will be next to the Mach 5 gun. But then when we want to go orbital speeds, Mach 25, that will be a physically larger gun. That'll be 2-ish meters in diameter and something like 10 kilometers long. That's the smallest space launch system we imagine that would fire like somewhere between 1 to 2 tons of projectile, Mach 25, and get something like a couple 100-kilogram payload into orbit, 500-ish kilograms of payload into orbit. If we go along our sort of like current tech dev timeline thing, something like 8 years, something like that to space launch, I think would be I would say kind of a conservative estimate. If we got a really great financial partner that was able to like put in a lot of money and make our lives easier, let us skip steps, then we could do it in something like 4 years, I think, 4 or 5 years. Right now, we're doing a lot of government contracting. Government contracting is reliable money, but it's not fast money. It takes a lot of work to get the money. So we have to do products, and that's fine. It's in some sense it's good. They have high standards for quality. So we're building things that we rely on, that we trust.